Hello, I'm glad to see you again at our course on hypersonic dynamics. Today we have lecture number 9, and uh, today's lecture today's lecture topic, uh, time matching finite different method. Okay, so let's start. And let us return to the roadmap in this slide and scan over the items discussed so far in our course. Starting with the basic hypersonic shock relations in lecture 2, we have covered all of the left branch of this slide and most of the second branch, down to and including the method of characteristics. These sections of the roadmap and hence all of the preceding discussion in our course pertain to the state of the art in hypersonic aerodynamics. I will say prior to 1966. Yeah, so old. Maybe for younger students. However, still discussing would have been inhibited by the then existing severe difficulties in obtaining blunt body solution. This solution was obtained by means of a time-matching finite difference technique that greatly simplified the calculation of flows over blunt hypersonic bodies. Indeed, the general idea of using time matching methods to calculate steady flow fields, for a whole host of different problems, and is now a major endeavor in computational fluid dynamics. The situation has changed so rapidly that the hypersonic blunt body problem, which in the 1950s and early 1960s was one of the major research problems of the day, with millions of dollars and the efforts of the scores of researchers spent on its solution, is today an extended homework problem in several university courses in computational fluid dynamics. Okay, so because of the importance of the blunt body in hypersonic aerodynamics application, and because of the efficiency and power of the time matching technique used to solve such blunt body flow, both will be discussed at length in this module. Also, with this section, we move to the right-hand column of our lecture roadmap in this. Yeah, please. On a practical basis, the blunt body is a particularly important shape in hypersonic aerodynamics. Because all hypersonic vehicles have blunt noses, right? To reduce aerodynamic heating. And we all know that such heating is a driving design factor for most types of hypersonic vehicles. However, on a heuristic basis, we can demonstrate the viability of a blunt body in reducing aerodynamic heating as follows. Consider a hypersonic vehicle at high altitude and high velocity, and hence with large values of potential and kinetic energy. Imagine the vehicle return to the ground at zero velocity. And hence, the potential and kinetic energies are now both zero, right? Where has all of the energy gone? The answer is into the air and into the body. The mechanism for heating the air is in the part of the temperature increases across the shock wave. On one hand, if the body were blender with a sharp nose, the shock wave would be weak. Hence, less energy would go into heating. And the air, yes, heating the air, and then the bow shock wave would be strong, right? Hence, more energy would go into the heating the air and less would be available to heat the body, right? On this physical argument alone, we can see why a blunt nose reduces the aerodynamic heat into a body. The point here is that blunt body flow fields are an important part of the study of hypersonic aerodynamics. And clearly, a detailed knowledge of the flow in the blunt nose region is essential to the accurate prediction of the heat transfer distribution around the nose, as well as to the detailed structure of entropy layers created in the nose region. In turn, the properties of the blunt body shock layer, as well as the shape of the shock wave in the nose region, can have a strong impact on the body surface conditions for downstream of the nose. For all these reasons and more, the blunt body problem discussed in our present section or module is an essential aspect of hypersonic flow. So here we will treat the inviscid blunt body flow, which is particularly important for the prediction of surface pressure distribution, shock wave shape, entropy layer structure, and for the calculation of properties at the edge of the boundary layer. Okay? So let's continue our class. What made the hypersonic blunt body problem originally so hard to solve? And why is it an almost routine calculation today? To answer this question, let us examine some physical aspects of the blunt body shock layer. Consider the steady flow over a blunt body moving at supersonic or even hypersonic speed, as shown in this slide. The shock wave in front of this body is detached and calm, right? Ranging from a normal shock wave right at the nose, okay? And becoming a weak Mach wave at large distances from the body, correct? So, hence, this single shock wave represents all possible oblique shock solutions for the given upstream Mach number, or we have in our case Mach sub infinity, right? With the wave angle ranging from beta may be changed from pi over 2 up to beta equals mu. What means mu? Mu here in our lecture is a Mach angle, right? Behind the normal and nearly normal portions of the shock wave, the flow is subsonic, whereas behind the more oblique portion of shock wave, the flow is supersonic. Are you agree with me? So hence, the blunt body shock layer is a mixed subsonic and supersonic flow, where the subsonic and supersonic regions are divided by sonic lines, shown as the dashed lines here in our slide. In the steady subsonic regions, the governing oil equation with, I hope you remember, d to d t must equal 0, are mathematically elliptic, whereas in the supersonic region, these same equations are mathematically hyperbolic. Okay? Okay. So the same Euler equation obviously apply in all regions of the flow field. However, their elliptic nature in the subsonic region means that the flow at any given point depends simultaneously on the properties at all other points in the subsonic region, and in a particular on the conditions along the total boundary of the subsonic region. In contrast, their hyperbolic nature in the supersonic region means that the flow at any given point depends only on the properties of the other points that are contained with the domain of dependence, bounded by Mach lines reaching upstream from the given point. And this situation is a partial answer to the question posed at the beginning of this module. Any theoretical or numerical technique suitable for the exact solution of the subsonic region is improperly posed and hence falls apart in the supersonic region, and vice versa. As just described, in the early days of hypersonic, its beginning of 60s, this mixed nature of the blunt body flow field made a consistent exact analysis valid for both the subsonic and supersonic regions, exceptionally difficult to obtain. And this situation changed dramatically, namely in middle of 1966, when Moretti and Abbott published the first truly practical supersonic blunt body solution. This approach utilizes a time matching, sometimes called time-dependent, finite difference solution of the governing unsteady Euler equation. Starting from arbitrarily assumed initial conditions and calculating the steady flow field as an asymptotic limit at larger time. Hence, a time matching approach starting from assumed initial conditions is a properly posed mathematical problem in all regions of the flow and allows the solution of both the subsonic and supersonic regions simultaneously with the same numerical technique. And today, the time matching approach is always used for the exact solution of blunt body flow field. The calculations are considered routine, and every major aeronautical company and laboratory has one or more versions of their standard blunt body computer program for this purpose. Because of the importance of these time matching solutions to modern hypersonic aerodynamics, the general purpose is outlined next. And here we will follow the philosophy as originally said, forth by Moretti and others. However, the Lux vendor finite difference technique was employed too, which later was superseded by a simpler version developed by McCormick. By the way, McCormick's explicit predictor correction finite difference method was widely used throughout the 1970s up to end of 80s. Today, it remains the most graduate student-friendly time matching method available because of its simplicity. And hence, it will be utilized here for our solution to the blunt body problem. For simplicity, assume a two-dimensional flow. The governing unsteady Euler equations you can see in this slide. Yes? To solve this equation for the blunt body flow field, the following steps can be followed. Initially, we should start with the next. We are considering a given body shape. And hence, this is a direct solution. That is, we are calculating the flow field and shock wave shape for a given body. Second, assume the shock wave shape and shock detachment distance. Cover the flow field between the shock and body with a series of discrete grid points as shown on figure A on the left part of the slide. In this figure, the body shape is specified as B function from Y, B function of Y, okay, independent in time. The shock wave shape, which is initially assumed at time when t equals 0, will change with time and is given by S as a function of Y and T. Y and T. So here the P and S are the S coordinate of the body, and S means shock wave respectively. Okay? Next, step 3, assume the flow field variables, in our case, rho, U, V, and P, at each of the grid points shown in the same figure A on the left part of this slide. This assumed flow field will be considered as initial conditions at time equal to 0. Next, step 4, calculate the flow field at the next step in time by means of an appropriate finite difference solution. As already mentioned earlier, during the 1970s up to 80s, the most popular finite difference technique for this purpose had been the explicit predictor corrector approach of McCormick. Because here the y coordinate remains the same in both the physical and the transformed space. So then the top and bottom of the rectangular space represent the downstream boundary and center line, respectively. In this fashion, the curvilinear grid in the physical space, as you can see from the left part of this slide, is transformed to the rectangular grid in the transformed space, as you can see on the right side. Because the finite difference calculations are performed on this rectangular grid on the right side, is also called the computational space, right? So, next 5 steps, for convenience, Moretti and Abbott also transform the dependent variables as P and R in the logarithm measurement. So, psi will be equal logarithm P minus gamma coefficient times logarithm P, or simplify P minus gamma R. Okay? Also, we can define as a C, it's zeta minus 1 times dp over dy minus zeta cotangent theta. So we can define the W component for the shock wave velocity is ds to dt, and B as this simple expression. Okay? In terms of the just transformed dependent and independent variable, our equation becomes the following. And you can see this on the right side. First, equation of continuity. X momentum, Y momentum, and equation of energy. But you should be known that these equations have been written with the time derivatives on the left side, and all of the spatial derivatives on the right side, for reasons that will be clear in the nearest shot. Okay? So also, we should know that the transformed equations are to be evaluated in the computational space, as you can see on the right side of the slide. Once the flow field variables are obtained at the grid points in this computational space, then the results can be directly carried to the corresponding grid points in the physical space, as you can see on the left part. But you should know that whereas the computational space is fixed, independent of time, so the shock layer thickness in the physical space is varying with the time, because the shock wave is moving, constantly changing the local shock detachment distance. In our case, it's distance d. And this means that the grid points in the physical space are moving. And only in the steady state obtained at large times do the shock wave and grid network in the physical space become stationary. The moment of the shock wave, that is the varying shock layer thickness with time, is accounted in our next equation, while the term of P, which contains the local shock wave velocity W, and in the steady state, W becomes 0. The boundary condition along the body, in our case it means zeta equals 0, is the usual inviscid flow condition that the velocity must be tangent to the surface. And that is, we may write that speed v times normal vector must equal 0. In our case, normal vector n is a unit vector which is normal to the surface, right? To implement this boundary condition within the context of the blunt body problem, Moretti and Abbott used a local, unsteady, and one-dimensional method of characteristics approach, written in the local normal direction at the body, much along the lines of the treatment of the shock boundary condition, as already described a bit earlier. except now the boundary is stationary. So, or the body is fixed, okay? At the end of the pre-final step, both the x and y components of the velocity u and v, right, will be obtained at the time t plus delta t at the given grid point on the body. In our case, as labeled as point 1, yes, point 1 in this slide. These components add vectorially to yield the vector velocity v at point 1 on the surface, as sketched in our slide, right? In general, vector v will not be tangent to the surface, and that is, the boundary condition will be violated. And we have to modify the boundary calculation to force our vector v, look at this on vertical part, to be tangent, right, to the surface, tangent to this surface. Another way to state this is to consider the component of v should be normal to the surface, namely v sub f, okay, in our slide. In general, this vector v sub f will be some finite value obtained by the process. And we need to make, in our case, v sub m equal or 0 in order to satisfy the body boundary condition. And to accomplish this, let us send a local or finite one-dimensional isentropic expansion or compression wave away from the surface at point number 1 of sufficient strength to cancel, namely v sub f. But we should note it here that at the end of the pre-final step, in addition to the velocity, values of pressure, density, etc. at this point 1 will also be obtained at time t plus delta t. For example, let us designate the resulting pressure of the grid point 1 at that time t plus delta t and name as a p sub o. However, by sending a traveling finite wave along normal to cancel v sub m, all of the other flow properties at this point 1, okay, will be slightly changed by the traveling wave. And that is, the pressure at point 1 after the wave interaction will be denoted as the P sub u. Similar definition holds for the T old, T new, R old, and R new, etc. Everything around at the point 1. Return now to our imaginary finite wave traveling away from the surface in this slide. In the case shown in figure A, where v sub m is directed away from the surface, the finite wave should be an expansion wave, because the mass motion induced by an unsteady expansion wave is in the opposite direction to the propagation of the wave, and hence canceling v sub m, right? After the expansion wave does its job, the new pressure at point 1, denoted, I hope you remember, P sub nu, is less than P sub O, because the pressure decreases through an expansion wave. Are you agree with me? Nice. So let's examine right figure B. If we were directed into the surface as shown, look here, B vector, and hence V sub m were into the surface. The finite wave should be a compression wave because the mass motion induced by an unsteady compression wave is in the same direction as the propagation of the wave, and thus canceling V sub m. Okay? Now, after the compression wave does its job, the new pressure at point 1, P sub nu, is greatest of P sub volt because the pressure increases through a compression wave. Okay? So, written in terms of the standard nomenclature for unsteady waves, we can have these two equations on the left part of our slide. Here the P4 and A4, and so as a T4 are the pressure, speed of sound, and temperature in front of the propagating wave. Here we have U sub stretch. This is as induced mass motion at arbitrary point inside the wave. And two components, P and T, are the corresponding pressure and temperature at that point. The plus and minus signs correspond to a compression wave and an expansion wave, respectively. And with the plus and minus nomenclature, the velocity U stretch is taken as positive in both cases. So applied to our discussion here, our equation we can rewrite, as you can see on the right side of this slide. Okay? So here we have V sub m is taken as a positive number in both the cases shown in this slide. The plus sign corresponds to the figure B, and the minus sign corresponds to figure A on the left part. So in summary, the flow properties at the body can be calculated from the internal flow algorithm using one-sided differences, giving as P sub O and T sub O, etc. Okay? Then the precise flow tangency condition at the body is enforced by expanding or compression the flow through the finite unsteady wave of strength just sufficient to cancel any finite component of velocity which is perpendicular to the wall. I understand this now. Right. So this yields slightly modified flow values at the wall, namely P nu and T nu, and so on. In turn, these are the final values of the flow field variable at the wall at time t plus delta t. So we may write as a P from t plus delta t, it will be as a P sub nu. The same t from t plus delta t, it will be as a T sub nu, etc. Right? So returning to figure B on the right side, the downstream and center line grid points, the top and bottom from the rectangle in this figure, they are easily written as follows. At the downstream boundary, The flow properties at the boundary grid point are simply obtained from the linear extrapolation from the values at the adjacent internal grid point. This is sufficient as long as the downstream boundary is taken far enough downstream to be supersonic all along the boundary. And this is an important consideration because extrapolation of any order is a properly posed supersonic boundary condition, but an improperly posed subsonic boundary condition. And hence, if any of the grid points along the downstream boundary are subsonic, and extrapolation is used to obtain the flow properties at these points, numerical instabilities are usually encountered. So, in regard to the center line boundary condition, for a two-dimensional or axisymmetric flow at zero angle of attack, the center line is the line of a symmetry. In such case, the usual symmetric conditions are employed, right? And namely, we can say that the dp over dy, it will be as a dt over dy, or du over dy, and all of them must be equal 0. In terms of our numerical calculations, these conditions are written as next line, referring to the nomenclature of our slide. So P for next step j plus 1, it's a P for previous j minus 1. For step before, T next step j plus 1 as a T from the previous step, T j minus 1. The same as for U j plus 1. It's the same as a U j minus 1. Because the y component of velocity v changes sign as the center line is crossed. The symmetry boundary condition on v will be described very simple. V for next step j plus 1, it will be negative values v as a j minus 1. And these symmetry conditions are sufficient to form the forward and rearward differences at grid points along the center line, and thus allowing the use of the usual internal flow algorithm to calculate properties along the center line. And that is to allow the calculation of our P sub j, T sub j, U sub j, and etc. So the stability criterion on the delta t, it will be as the delta t must be no higher than the minimum values delta t sub x and delta t sub y. Delta t sub x is difference delta x over u plus a, and delta t sub y analogically delta y and related to the v plus. These three equations constitute a version of the Courant-Friedrich-Levy or CFL criteria, Courant-Friedrich-Levy criteria, which governs the stability of the explicit methods dealing with hyperbolic equations. On a physical basis, delta t sub x is the time it takes a sound wave to travel between two adjacent grid points on the x direction. Okay? And so on, the delta t sub y is a similar time in the y direction. So our first equation, delta t no higher than minimum delta t sub x and y, say that the allowable time step in the explicit method should be less than this step should be less than or at the best equal to the minimum of these two times. Okay? So the CFL or Courant-Friedrich-Levy criterion was first derived on the basis of linear partial differential equation. And therefore, for the non-linear Euler equation are to be interpreted as a guideline only and not as precise condition. Remember. And hence, in practice, delta t is chosen such as this expression on the bottom, minimum of both of these values. Here, coefficient k is less than unity, typically on the order of O.5 up to O.8. A particular value of k suited to a particular application is usually determined by trial and error. Okay? Now, let us examine some typical results for hypersonic blunt body flow obtained by means of the time matching procedure. Such results are given in this slide. For the flow over a parabolic cylinder at zero angle of attack, with the exception of the first figure on the bottom, which is an axisymmetric parabola. In particular, first two, yes, this upper figures illustrate the time matching mechanism. And in this slide, the unsteady box shock wave motion is shown for the case where the m infinity equals 4. The fixed parabolic cylinder is shown at the right. And 4 different shock shapes and locations are shown, corresponding with 4 different times during the calculation. The shock labeled 0 dt is the assumed shock wave shape and location at time where t equals 0, part of the assumed initial condition, right? The shock labeled 100 dt is the shock shape and location after executing the preceding time matching technique for 100 time steps. The shock waves as 200, 300, and even 400 dt are also shown here. But note that at early times, the shock wave moves rapidly. But after 300 time steps, wave motion has decreased considerably. And the shock is essentially steady. The shock waves for 300, 400, and 500, these 4 time steps, are virtually the same as shown in this slide. And the result shown at namely 500 delta t is essentially the final steady state shock wave shape and location that is the desired result. The time matching behavior is further illustrated in this slide, which gives the time variation for the pressure at the stagnation point. But note that the pressure changes very rapidly at early time during the time matching procedure. But at larger times, it asymptotically approaches the steady state value. And again, emphasis is made that we desire a solution to the steady state flow field, and the time matching procedure is simply a means to that end. it in carrying out such time matching solution. By the way, my student used to generate large amounts of computer printout for a given case. I sometimes jokingly told them to tear off the last sheet and keep it and throw out the result, the rest, because the last sheet contains the solution to the problem. So today, the output appears graphically on a computer screen. Some steady state results are shown in this plot. In this figure, the steady state surface pressure distributions are shown for Mach equal 4. And it's a sphere, black sphere, Mach equal 8. The exact time matching finite different results are shown as a solid curve. And also, for the sake of comparison, the symbols give the modified Newtonian prediction. Note that, as already discussed in earlier lectures, okay, the Newtonian results are not very accurate for a blunt two-dimensional body. And we see in this slide that Newtonian results underpredict the exact numerical results downstream of the immediate nose region. This is not the case for an axisymmetric body, as shown in this slide. And here the surface pressure distribution is given for an axisymmetric parabola. The solid curve gives the exact numerical results, and the open squares are from modified Newtonian. And here, agreement between the exact result and Newtonian is quite good. And again, emphasizing that Newtonian theory appears to be more applicable to three-dimensional rather than two-dimensional bodies. In this slide, some additional data are shown, namely the results of Lomax and Inouye, which were obtained from a numerical steady flow inverse blunt body solution. These data are shown here to emphasize a particular advantage of the time matching method. This recall that for gamma equal 1.4, sonic flow on the surface occurs when we have ratio P over P naught equal 0.528. Examining in this figure, we know that the inverse blunt body solution is discontinuous in the vicinity of the sonic point. A problem encountered by all steady flow blunt body techniques prior to 1963. In contrast, the time matching procedure gives results for downstream of the body sonic point. Indeed, as far as one wants to go downstream. As a final example of the present technique, this slide shows the steady state shock shapes and sonic lines for a parabolic cylinder at Mach 4 and Mach 8, obtained by means of the time matching procedure. Note that as m infinity increases, the shock wave moves closer to the body, and the sonic points on both the shock and the body move closer to center line. All standard physical behavior for blunt body flow, right? And furthermore, observe that the m infinity increases, the sonic point on the shock moves down faster than the sonic point on the body. And thus, the sonic line actually rotates in a counterclockwise fashion. as the Mach number increases. Okay? Some interesting details of the physical aspects of the sonic line behavior are given by Heiss and Probstein and are summarized in this slide, taken from some publications. In this slide, qualitative results are sketched for two cases, namely the flow over and two-dimensional circular cylinder and the flow over an axisymmetric sphere. Also, the shapes are the same. The behavior of the sonic line is not. For example, in figure A, on the left side of the slide, the sonic line is shown for both the cylinder and the sphere at low supersonic Mach number. The sonic point on the shock is much higher than on the body. And the angle made by sonic line at the body, in our case omega sub beta, right, is acute. For the cylinder, as the Mach number increases, the sonic points on both the shock and the body move closer to center line, and the sonic line becomes more curved, as shown in next figure B. Look at sonic line on the middle, right? So the sketch shown in this figure pertain to a Mach number of approximately 2 and great, and a bit great, between 2 and 3. For the cylinder, the angle omega b always remains acute, no matter how high the Mach number. So we should know that the sonic lines at the body in this slide for a two-dimensional parabolic cylinder are consistent with this fact. Figure B also pertains to the case of a sphere, but only for the limited Mach number range approximately between 2 and 3. At higher Mach numbers, as shown on the next right figure, C, for the sphere we have omega sub b becomes obtuse. And we should notice that this slide also illustrates the limiting characteristics and how they change with Mach number. I hope you remember, by definition, the limiting characteristic is the locus of the point, each of which has only one point of the sonic line in its zone of action. For example, in this slide, the flow is locally supersonic at each point downstream of the sonic line. However, in a figure A, imagine a left-running characteristic line, in our case, Mach wave, initiated at some point on the body that lies between the sonic line and the limiting characteristic, between the sonic line down and limiting characteristic as a dotted line. This left running characteristic will propagate upward and to the left and will intersect the sonic line somewhere between the body and the shock. When we move downstream to the limiting characteristic itself, the left running characteristic will only intersect the sonic line at the shock point. And only when we move downstream of the limiting characteristic will the left running characteristics no longer intersect the sonic line. The physical implication of this is that also the flow region between the sonic line and the limiting characteristic is totally supersonic. Disturbances produced in this region and will propagate to the sonic line and can affect the entire subsonic portion of the flow. Similar arguments holds for the cases shown in figure B and C. This is why, in last lecture, repeated warnings were given that the initial data line for a method of characteristic solution over a blunt nose body must be taken downstream of the limiting characteristic, not just downstream of the sonic line. Okay? Another interesting physical aspect of hypersonic blunt body flows is the location of the stagnation point and the point of maximum entropy. For a symmetric body at zero angle of attack, the stagnation streamline and the stagnation point are along the center line, as you know, center line and stagnation point in figure A, right? And this streamline crosses the bow shock at precisely the point where we have beta equal half pi. That is, it crosses a normal shock, and hence the entropy of the stagnation streamline in the shock layer is the maximum value, right? In contrast, consider the axisymmetric cases shown in figure B and C, as an axisymmetric flow can be produced by a non-symmetric body, an angle of attack, or both. In these cases, the shape and location of the stagnation streamline and hence of the stagnation point are not known in advance, and they must be obtained as part of the solution. Moreover, the stagnation streamline does not pass through the normal portion of the shock wave, and hence it is not the maximum entropy streamline. The relative locations of the stagnation streamline and the maximum entropy streamline for two nose shapes are shown in B and C figures. That the stagnation streamline is always attracted to the portion of the body with maximum curvature, whereas the maximum entropy streamline will turn in the direction of decreasing body curvature. Okay? A further interesting point concerning entropy, and one with particular consequence to the time matching procedure, is as follows. Consider the entropy equation, as you can see here on the left, and when applied it at stagnation point, in our case, U and V and W should be equals one another and will be zero. And so we can use as this simple equation, ds to dt should be equals. And now return to figure A on the left side of this slide, which shows the physical plane for a symmetric blunt body at zero angle of attack. And now consider the stagnation point, which occurs on the theta line, yeah, in this part. And our equations in this body dictate that at the stagnation point, the initial conditions, in our case t when equals zero, for a time matching solution cannot be chosen arbitrarily. Indeed, the proper steady state value of entropy must be used because it will remain constant at the stagnation point throughout the time matching procedure. Okay? Okay. However, this is no problem for the symmetric case. We know in advance that the steady state conditions at the stagnation point are identical to the stagnation condition behind a normal shock wave, which are easily calculated for the normal shock relation. And therefore, the proper initial conditions at time when equal zero at the stagnation point on the blunt body in figure A, left part of the slide, are simply the stagnation condition behind a normal shock wave. And this is demonstrated in this slide, where the initial value of P naught at time t equals zero was indeed chosen as the proper steady state value. After going throughout the massive variation shown in this slide, P naught finally approaches in the limit of large times, and the value is started with the t equals zero. Okay? For the axisymmetric case, where the location of the stagnation point is not known in advance, chances are that none of the chosen grid points will correspond to the stagnation point, and thus the problem is not encountered. The example chosen in this section to describe and illustrate the time-matching solution of hypersonic blunt body flow, and was a two-dimensional body at zero angle of attack. And this was done for simplicity, as well as to underscore the basic ideas and philosophy of the method without cluttering our discussion with tedious details. Okay? The extension to three-dimensional flow is straightforward. Also, the amount of details and tedious computation increases by almost an order of magnitude. The three-dimensional shock wave was treated as a discontinuity and moved in space during the time-matching procedure. In the physical space, a spherical coordinate system was used in the blunt nose region of the body, matched to a cylindrical coordinate system for the remainder of the flow field. The physical grid is presented namely in this slide, which shows both the symmetry plane and the cross-flow plane. Okay? This physical plane was transformed to a three-dimensional rectangular box, analogous to the transformation shown in this slide, for the finite difference calculation, along with the appropriate transformed equation. A total of, say, 84,000 and more than 800 grid points were used in the calculation, which was carried out on CDC Cyber 2003 supercomputer for that time, as a sample of the result. And this slide illustrates the final steady-state shock wave at Mach equals 16.25 at the angle of attack of 39.8 degrees. And this slide gives the centerline pressure distribution over the bottom surface for the same light condition. In this slide, the solid and dashed lines are calculations for gamma 1.4 and gamma 1.2, respectively. The symbols are flight testing data from the space shuttle itself. Excellent agreement is obtained, as you can see here. But note that the pressure distribution is relatively insensitive to changes in gamma. And these results are presented here as the epitome of time-matching solution to inviscid hypersonic blunt body flows. On this note, we conclude our discussion of exact solutions to hypersonic blunt body flow. The time matching solutions discussed here represent a substantial milestone in the progress of aerodynamics theory, not only for hypersonic, but for the whole spectrum of aerodynamics. I think it's enough for today. And I hope you enjoyed today's lecture. And moreover, I'm looking forward to seeing you next time to continue our study, our favorite course. Okay? Bye.